The code is almost done with the system initialization. The last thing it needs to do is to release any other cores in the system from reset. Once they are released, they will start executing this boot code. The code checks to see if there are more cores in the system, and if not, it will branch to the end of this section and return. The code uses A3 as a counter to decide if it has released all remaining cores. The code checks for a cluster power controller by seeing if the address was set for the CPC in the CPC register block. If the value is 0, there is no CPC, and the code will skip ahead and just release the next core so it can begin execution. Remember, this code is only executed by core 0. The core will send the power-up signal to each other core in the system. The code will use the cluster power controller to do this. The code needs to place the number of whatever core it wants to power up into the core other addressing register. To do this, the code moves the number of the core it wants to power up into A0. Next, the code shifts the value to the left into the range of the core number field of the core other addressing register. Then the value is stored to the core other addressing register by computing the offset into the CPC registers and using R30 that contains the base address of the CPC registers. The first register in the local control block is the CPC local command register. This register is used to power up or down the core. It has a command field called CMD, which is the first 4 bytes of the register. Right now, we're interested in powering up the core. The core loads the command into A0 and stores it to the command register of the CPC. This will power on the core, which will begin executing this boot code from the beginning. Next, the code sees if there are any other cores in the system by comparing the current core number with the highest core number. If there are other cores, the code loops back to power up the next core. The core number is incremented for the next iteration of the loop in the branch delay slot. When the code has looped through all the remaining cores, it returns. Here is the code that will be branched to if there was no CPC. Since there was no CPC, cores other than core 0 will have been held in reset. This loop will set the other core's value so it can go into the other core's GCR reset register. It copies A3, which was initialized to 1, into A0, then shifts that into position. It uses A0 to set the core other value of the core that's going to be released. It then stores a 0 into the GCR CO reset release register to release that core from reset. It continues looping until all cores are released. Once all cores have been released from reset, the code returns to start.s. Next, the call calls the init function that joins the core to the coherent processing domain. The core first checks to see if it is on a coherent processing system. If not, it will branch to the end of the function and return. The core local coherence control register controls the entry and exit of the core into the coherent domain. Bits 0 through 7 represent a coherent requester within the system. The code sets to 1 the first 4 bits of A0, then stores it in the core local coherence control register. This enables the 4 cores possible in this system to communicate via interventions to this core. Notice the EHB instruction. It is needed to clear an instruction hazard barrier and make sure the core local coherence control register write has taken effect before the code continues. Next, the code will wait until the other cores in the system have joined the coherency domain. The code initializes A3, which it will use as a loop counter to 0. Next coherent core is the label which the code will loop back to and join the next core domain. The code sets up the core other addressing register with the core number it wants to join with. It first stores the value of the core to A0, shifts it into the upper 16 bits, and then stores it to the core other addressing register. The code now reads the core local coherence control register of the other core. Remember how the code set this core's core local coherence register to enable interventions from other cores, thus entering the domain. The code now needs to wait for the other cores to do the same. Once the other core has joined, the code checks to see if there are more cores to wait for, and if there is, it branches back to the next coherent core label. It also increments the core count. When all the cores have been waited for, the code returns to start.s. The init VPE1 is called if the core is an empty core. The code initializes the second VPE of an empty system. It first checks to see if there is an additional TC to bind to a second VPE, and then if there's a second VPE. If neither is true, no action is required, so the code will jump to the done point. The setup for the second VPE will require access to some registers that are usually non-writable. To write to these registers, the code needs to enable virtual processor configuration. To do this, the code reads the MVP control register. It then sets up the VPC bit, writes it back to CP0, and executes an EHB to ensure that the write has been completed before it continues. Defines are created to make it easier to follow the code. NTCS is a register that will hold the number of TCs in the system. NVPEs will hold the number of VPEs in the system, and TC will hold the current number of the TC being initialized. The code reads the MVP config register. Then it extracts the highest TC number and the highest VPE number into the registers noted above. Next, it initializes the TC count to 0. This loop will initialize the remaining TCs in the system. The code sets up the target TC field in the VPE control register by reading the register, inserting the TC number into the targ TC field, and writing it back to the VPE control register. Doing this controls which TC the MFTC0 and the MTTC0 instructions write to. This is how the CP0 registers of a TC other than the one executing the code are written. It executes an EHB to ensure the write took effect before it continues. The code checks to see if the current TC in the loop is TC0. If it is, it branches forward to the next section since it doesn't want to reinitialize itself. The TC should be halted before the code starts changing its configuration. To do that, a 1 is placed in V0, then moved to the TC halt register. The code executes an EHB to ensure the move has taken effect. The code tests to see if this TC is the first TC bound to a VPE. If not, it branches to the binding code. This is done because this example sets up only one TC to execute per VPE. If there are more TCs than VPEs, the branch will be taken and the TC will be bound to the last VPE in the system. The branch delay slot is used to save the number of VPEs in the A2 NVPEs register. The next step is to set this TC to the only runnable TC on the VPE when an exception or error happens. This effectively sets TC1 to run exclusively on VPE1 when an error or exception happens. To do this, the XTC field in the VPE comp0 register is set to the TC number. The code reads the VPE comp0 register, inserts the TC number into the XTC field, and writes it back. The code will now bind the TC to the VPE. It does this by reading the TC bind register, inserting the VPE number into the current VPE field, and writing it back. The code sets this TC to prevent it from taking interrupts and clears all other status and control bits in the TC status register. It does this by setting the interrupt exempt bit IXMT in V0, and then it moves it to the TC status register. The code then initializes the TC's GCR registers using the same method used in init GPR.S. Next, the code checks to see if there are any more VPEs to initialize. It does this by checking to see if the number of VPEs left is less than the number of TCs. If it is, all the VPEs have already been initialized, so the code branches forward to done VPE, where it will check to see if there are any more TCs to initialize. The code will now initialize the VPE. In fact, on current cores there are at most 2 VPEs, so this code will be executed only if there is a second VPE. First, the code makes sure multi-threading is disabled. It needs to do this because only one TC should be executing this code at a time. It does this by clearing the TE bit in the VPE control register. The code reads the register, inserts a 0 into the bit, and writes the register back. The code checks to see if this is TC0. If it is, it branches around the initialization to the end of the function because it has already been done for TC0. The code needs to make sure that no TC is running on the VPE it is initializing. It does this by reading the CP0 VPE comp0 register of the VPE it is initializing and inserting a 0 into the Virtual Processor Active or VPA field. It also needs to make sure that it is the master virtual processor by setting the MVP bit. This enables the writing of registers associated with the VPE. Then the code writes it back to the VPE comp0 register of the VPE. The code copies the status register of the running TC to the status register of the TC being initialized. Initialize the error PC to a dummy value, clear the cause register, copy the config register of the running TC to the config register of the TC being initialized. The code then initializes GPR23 of VPE1 to the core number it is on. It does this by reading the eBase register and extracting the CPU num field. It then copies the CPU num to the TC's GPR23. The code programs the TC's reset vector so that when it is set to run, it will start executing the boot code. It loads the address of the reset vector from the label created in the linker file. It sets bit 29 to convert the address to a kseg0 address, so it will execute from a cacheable address. Then it writes the value to the TC's restart register. The first thread for this VPE is ready to run, so the code sets it to start running. However, it will not run until all TCs have been initialized and the code exits the VPE config mode and enables virtual processing, which it does at the end of this function. The code reads the TC status register and enables the TC for handling interrupts by clearing the IXMT bit. It also activates the TC by setting the A bit. It then writes the value to the TC status register. Now the code unhalts the TC by clearing the H field in its TC halt register. The code then sets the virtual processor active bit in the VPE comp0 register to activate the VPE and allow the TC it has just initialized to start running. It does this by reading the initialized VPE's VPE comp0 register and setting the VPA bit, then writing it back. Next, the code will check to see if there are any more TCs in the system to initialize. It adds 1 to the current TC being initialized and then tests to see if it is still within the limits of the number of TCs that are in the system. If it is, it branches back to the top of the loop. This is the path the code falls through when there are no VPEs or TCs left to initialize. The code needs to enable virtual processing and take the processor out of virtual processor configuration mode. It will read the MVP control register, set the EVP bit, and clear the VPC bit, and then write it back to the MVP control register. Now for some cleanup of the code to remove the pound defines it created in the beginning of this file. This function is done and now returns to start.s. The assembly part of the initialization is complete. The code is now ready to call the main function. The code sets the return address to the all-done function. This is done in case the main function returns. Normally, the main function never returns. It usually starts up the OS, and the OS handles everything from there on, including the halting of the system. Just in case something goes wrong, we don't want just any random code to execute. The all-done function is just a simple loop that will cause the processor to spin forever. Next, the address of main is loaded into A1, and the value of A1 is moved to the CP0 error exception PC. This is the return from exception address. To explain what is happening, when a MIPS core boots, it is in exception mode, so all of the code that has executed so far is part of the boot exception process. At the end of this boot exception processing, the code will use the error return instruction to change the mode to normal processing and start executing instructions at the address stored in the error exception PC. The variable numcores is a global variable used in the C code. This is an example on how you would initialize a global variable in assembly to be used later in C. First, the address of the global variable numcores is loaded into A1 and converted to an uncached address. A0 is set to the number of cores in the system by adding 1 to the highest core number that was stored in R19. A0 is then stored in the address of numcores. The code places the arguments to main in the 4 argument registers. The use of these registers to pass arguments follow the C ABI calling convention. The arguments are the CPU number, the core number, the VPE number, and the total number of VPEs. ERED is called and will clear exception mode and start execution of the main function. The code in the main function gives you an example on how to synchronize all CPUs in a CPS before continuing execution of test code or starting an OS. Main starts out by declaring some local variables it will be using. Next, the code reads the value of the CP0 count register. The inline assembly code moves the count register value to the local variable temp. Then the code writes that value into the boot count array element for this particular core. The boot count array is a global variable array that will collect the number of cycles the boot processor took for each core. This is just an example of recording statistics from each CPU. The boot count is not used further in this example. Each core will report how many virtual processors are available on the core. The OS could use this to set itself up for each core. The code uses CP0 to do the synchronization for the rest of the CPUs. The code waits for each core to report the number of processors on the core. The code tallies the number of processors on each core and will use it later in this loop. Next, the loop will use the numCPUs variable to wait in turn for each CPU to report it is ready. The Malta evaluation board has a small display, and the code uses it here to report which core it is waiting for. The code writes a W to the display element that corresponds to the core being waited for. When a core reports it is ready, it will call the wait instruction, which will stop the core until the core receives an interrupt. It is CPU 0's job to send the interrupt to wake up the other cores so they can continue processing it. It does this by using the interprocessor interrupts that were set up in the boot MIPS code. The code first changes the segmented display by writing an I to the corresponding element for the core it is going to interrupt. Then it calls the setIPI function to send the interrupt. I'll talk about the setIPI function in the next slide. Once CP0 finishes this loop, it can continue to execute the test code and/or the OS. The setIPI function will send an interrupt through the global interrupt controller to a specific CPU number provided by the CPU num. The boot MIPS code sets up the GIC to write each interrupt to a specific CPU. Recall that interrupts 32 through 39 correspond to CPUs or VPEs 0 through 8. CPU 0 uses interrupt 32, CPU 1 uses interrupt 31, and so on. The pound-defined GIC-SH wedge sets up a pointer to the global interrupt right edge register. It does this by combining the address of the GIC register control block, which in this case is a hex BBDC0000, with the offset of the global interrupt right edge register of hex 280. The value written to the global interrupt right edge register has two parts. Bit 31 is set to indicate that the code is sending the interrupt signal. Bits 0 through 30 determine which interrupt signal will be sent to. The code calculates the proper interrupt by using the pound-defined first IPI as a base interrupt number and adding the CPU number. Once the value is written, the corresponding CPU will receive the interrupt, which will wake it up to continue executing code where it left off. All processors other than processor 0 will stop and wait for processor 0 to synchronize them. Once the interrupt is sent, the processor will continue execution. First, the code makes sure that the interrupt source bit corresponding to its processor number is cleared by writing to the right edge register. Then it enables interrupts. Next, each processor will write an R to the segment display to indicate it is ready. Then it will write to the global array to indicate to processor 0 that it is ready. Next, interrupts are disabled. This avoids any race condition between testing of the start test array and the wait instruction. The code will loop, testing its element of the start test array and calling wait to wait for an interrupt sent by the processor 0. When any interrupt is signaled, the processor will wake up and enable interrupts so that its interrupt service routine can run and process the interrupt. The interrupt routine will set the start test element for this processor. By the time the code reaches this point, the interrupt routine will have run. The code will disable interrupts before it returns to the top of the loop. The top of the loop is where the start test array is checked, and just as before, interrupts need to be disabled to avoid a race condition. The start array needs to be checked because any interrupt could have terminated the wait instruction. This is the interrupt routine that will receive the interprocessor interrupt. Remember, an interrupt is sent by processor 0 through the use of the set IPI code as shown in the previous slide. The interrupt code shown here is in start.s. It is loaded at hex BFC00380, which is the general exception vector. Since the only interrupt generated by this code is an interprocessor interrupt, the code proceeds to clear the interrupt in the right edge register. The code loads the address of the right edge register into K0. Then it reads the CP0 eBase register and extracts the CPU number. Again, recall that interrupts 32 through 39 correspond to processors 0 through 8, so the code uses 32 or a hex 20 as the base number for the interrupt and adds it to the CPU number to get the correct IPI number for this processor. Next, the code writes the interrupt number to the right edge register to clear the interrupt. Now that the interrupt is cleared, the code will set this processor's element in the start test array. The code does this by loading the address of the start test array into K0. Then the code reads the eBase register, extracts the CPU number, and multiplies it by 4 because the array is an array of integers. Next, the code adds this index to the starting address of the start test array to get the address of the array element specific to this processor. The code then sets K1 to 1 and stores it to the array element. When the code returns from the interrupt, each processor will return from the wait instruction and look at its element of the start test array to see if it should continue. At this point, the booting of the processors is done. You can add your code here to run a test or call the OS boot up. This code displays the processor number on the display. It does this in a loop, so it will display for a time, then the next code will blank the display in a similar loop and go back to the top of the while loop. The effect will be the blinking of the processor number on the Malta display.